Let's take a look at the formulas in the electricity and magnetism chapters of the AP Physics book. Let's start out with the definition of resistance. R stands for resistance. Rho stands for resistivity. The resistance of a length of wire is measured simply in ohms, but the resistivity is ohms times meters. What this allows us to do is it allows us to compute the resistance of a length of wire based on the resistivity of the wire, the length of the wire, and the cross-sectional area of the wire. This formula is very useful for dealing with a length of wire. If I have its length and I have its area, cross-sectional area, which by the way is pi r squared, we want to make sure we're in SI, so length would be measured in meters, cross-sectional area would be measured in meters squared, and if I have the resistivity in rho meters, that's a property of the substance itself. From these three things I can calculate the resistance of the wire. Next, let's take a look at Ohm's law. Ohm's law is V equals IR. V stands for voltage, or potential difference, or sometimes it's even called EMF for electromotive force. Those are all the same thing. Those are all V. That equals I, which is current, in amps. And then R is resistance in ohms. And again, this is called Ohm's law. When a substance is ohmic, that means that it follows Ohm's law. In other words, the graph of voltage and current is a straight line. Next, we'll look at the definition of power. Power is current times voltage. Power in watts, and a watt is a joule per second, is equal to current in amps times voltage in volts. Remember that the definition of current is coulombs, its charge, per second. This next formula with C, here C stands for capacitance. And what we have is we have two different formulas, one for capacitors in parallel and one for capacitors in series. When we're working with capacitors in parallel, what we do is we simply add them together. We say, let me write it the way I wrote it in class, the equivalent or effective capacitance is equal to C1 plus C2 plus C3 and so on. What this formula is doing is trying to shorten that up. It's saying the capacitance in parallel is equal to the sum of each individual capacitor. Then, for capacitors in series, the way that we wrote it in class was that 1 over C equals, 1 over C1 plus 1 over C2, etc. And the formula on the formula sheet is trying to make that a little bit shorter. They're saying 1 over the capacitors in series is equal to the sum of 1 over each individual capacitor. So this can help you remember how to add in parallel and in series for capacitors. Next, they show us what to do with resistors. This is R sub S is resistors in series. If you're adding resistors in series, you simply add each individual resistor. Again, instead of writing all the plus signs, what they do is they say the sum of the resistors in series is equal to the sum, that's what the symbol means, of each individual resistor. And then for resistors in parallel, what we do is we take 1 over the sum of the resistors in parallel, or the equivalent or effective resistance, is equal to 1 over R1 plus 1 over R2, etc. And again, on the equation sheet, what they do is they write it like this. They say it's the sum of the reciprocal of each individual resistor. Now let's turn our attention to some formulas that have to do with magnetism. I remind you that over on the equation sheet there is a key that tells you what each variable stands for. So our next two formulas tell us about the force in a current carrying wire. FB equals QVB times the sine of theta. Now this is actually talking about an individual charge moving at a certain velocity, which is a very similar concept to current moving through a wire. Basically what this says is it says that the magnetic force on a charge, charges in coulombs, forces in newtons, is equal to the charge times the velocity in meters per second times the magnetic field sometimes called the B field. That's measured in Tesla, or T, and then times the sine of the angle between the magnetic field and the direction of the moving particle. In order for there to be a force, we need the direction of the field and the direction of the velocity to be perpendicular. Let's next take a look at this formula. FB equals BIL sine theta. So our first formula was for an individual point charge. The second formula is for a current carrying wire. So what we have here is that the magnetic force in newtons is equal to the magnetic field that's B, that's the symbol, the unit again is Tesla, times the current, I, in amps, times the length of the wire, that's cursive L, in meters, and then again, running out of room here, times the sine of the angle between the magnetic field and the length of the wire. Our next formula is for the amount or the strength of the magnetic field around a current carrying wire. So B is magnetic field. This mu sub naught, this is a constant. I is current in amps. And R is your distance from the wire. So, let's lift this up a little bit. If you have a current carrying wire with a magnetic field around it, you can find the strength of this magnetic field based on your distance from that wire. That's what this is saying, and based on the amount of current in that wire. The last formula that we're going to look at is this last one. We're going to skip these two. These two are for something called magnetic flux, which we will touch on later. But let's take a look at EMF equals BLV. This formula is for the voltage that is developed when we have a magnetic field a length of wire, and a velocity. So what we're doing is we're actually moving a current carrying wire through, or a potentially current carrying wire through a magnetic field. And what happens is we create a voltage in that wire. This is where the concept of a generator comes from. What a generator does is you take a loop of wire, you move it in a magnetic field, and you generate current. The units here, voltage is V, magnetic field is Tesla, length of wire is meters, and velocity is meters per second.